Hello, everyone. It's nice to see many people again this week. So today we have Guoqi Yan from the University of Notre Dame, who is going to talk to us about the generalized Tate diagrams of the equivariant slice filtration. Thank you.
Okay, thank you very much for the introduction, and thank you for having me here. So today I will be talking about the generalized Tate diagrams of the equivariant slice filtration. So let's start from the motivation. So the story of the computation of the equivariant slice spectral sequence start from Hopkins Ravenel's resolution of the Kervaire invariant problem. So in their resolution, they generalized the C2 slice spectral sequence invented by Dan Dagger to all finite groups, and they studied the C8 equivariant slice spectral sequence of this C8 spectrum. So if you haven't seen this spectrum before, so I will introduce this notation later. The C8 is a cyclic group of order 8. And later, Hahn and Shi showed that there are real orientations of the E theories by the real Bourdism theory. And we know that E theories are very hard to compute, but this orientation enables them to compute the homotopy fixed point, the C2 homotopy fixed point of E theory for all height, because the slice spectral sequence on the left-hand side is much easier to compute. And more generally, we can also understand the homotopy, the C2N equivariant homotopy fixed point of E theory using the equivariant slice filtration. So this equivariant method gave us a way to compute something in chromatic homotopy theory. So let's start from this motivational picture. So this is a C4 equivariant slice spectral sequence. And this is a motivational picture for Hopkins Ravenel's resolution of the Kervaire invariant. And it's also the motivational picture for our project. And our focus on this project is to understand systematically study the duality pattern in this spectral sequence. Because as we can see, so where I point at, the cone tip is origin, and everything to the right are the positive stems. And because this is a cone-shaped area, I will call this the positive cone. And the other part is the negative cone. And you can see that there is some dual patterns in this picture. So there is a above the diagonal line, there is a very simple region, the blue differentials, just one type of differential. And on the opposite side, there are also a very similar pattern, just blue differentials. And below the diagonal, there are more complicated differentials. But if we look at the opposite side, they look almost the same. And the focus of our project is to systematically study this duality between them. So let's introduce some background of our study. So recall we have the complex co-Bourdism spectrum MU. So the component space of MU is defined as the Tom space of the canonical bundle over BUN. And the structure map are just given by SC smash MUN to MUN plus 1. The C is the complex plane. SC is a one-point compactification of that. So topologically, this SC is just S2. And later, Landweber, Fuji, Araki, and Hu Krish explored a real analog of this story. So we can notice that the complex number has a C2 action by complex conjugation. And everything involved in the definition of MU, it has an induced C2 action from the conjugation. So for example, BUN is Grassmannian in C infinity, so it has an induced C2 action. And also as a Tom space, MUN has a C2 action. So as a result, we get some C2 equivariant structure maps as follows. So MUN has C2 action, MUN plus 1 also has a C2 action. Now here, C is regarded as a representation of the group C2, and it becomes the regular representation of C2 over the reals. So this is, as rho 2 is the representation sphere of the regular representation of C2. And this definition leads to this genuine C2 spectrum called real Borism spectrum, MUR. And this plays a crucial role in the slight spectral sequence and the solution of the Kervaire invariant problem. So now, start from MUR, we can lift this Quillen idempotent to a C2 equivariant map, and as classically, we can take colimit along the Quillen idempotent and get a summand called a BPR, the real Brown-Peterson spectrum. And this is C2 equivariant spectrum. We can apply the HHR norm of that. So norm is a functor from C2 spectra to C2N spectra. So if we norm this thing up, we get this normed up version of MU and the BP. So MU C2N is a norm of MUR to the bigger group C2N. And BP C2N is defined similarly. So let's look at some examples. So we can start from BPR and kill some generators in high dimensions. In the above degree 2, we will get a form of connective RTSK theory. And this is a very familiar example if you know some C2 equivariant homotopy theory. And now we have a C2 equivariant Baud class. So I added a bar to V1 to denote this C2 equivariant Baud class. After inverting this class, we get the periodic version of RTSKR theory. So this theory of height 1. And more generally, we can mimic the above process and get the Hopkins Ravenel theories of the following form. So D inverse BPC2N. So this BPC2N, as we talked about before, is a normed up version of BP. And similarly, we can just take quotients and inverse some higher Baud class. We get this Hopkins Ravenel theory. So these are the higher height analog of K theory. And so they model the Morava E theories. And the advantage of these theories is that we have the equivariant slight spectral sequence, which is computationally more accessible. So here's some background on the slight filtration. So let G be a finite group and X a G spectrum. Then there are two kinds of spheres that we can consider. So the first one is the permutation spheres. So here Sk is the k-dimensional sphere with trivial G action. And G mod H is a coset. So the G action on this thing is purely on the left factor. So it is actually a bunch of spheres permuted by G. And this kind of sphere is a sphere we use to build GCW complex or GCW spectrum. And the Posnikov sections are the universal arrows that kills maps out of this kind of sphere. So this is an equivariant version of Posnikov section. And we have another kind of sphere so rho H is the regular representation of the subgroup H. So we take M copies of that and induce it up. So this is an induced regular representation sphere. If we Q maps out of this kind of spheres of above certain dimension, we get a localization functor which sends X to Pn X, and this is the slice section. And this slice section will lead to the slice spectral sequence. By the universal properties, we get a tower under X. And this tower has very good convergence properties. the inverse limit of tower of this tower is just x itself, and the co-limit will be a point. So a fiber or the associated gradient is denoted by PNNX. So now the thing makes equivariant homotopy. One thing that makes equivariant homotopy theory computation hard is that their homotopy groups are ROG graded Mackey functors. So here is an example of a Mackey functor. So if the group is C4, then there are 3 abelian groups involved. We take so this is a zeros homotopy. So the C4 equivariant zeros homotopy, the C2 equivariant zeros homotopy, and the non-equivariant one. And they are connected by structure maps, restriction, transfer, and as well as the while actions. So now we have the slice tower, we can apply the Mackey functor value homotopy group to that. The pi underlying, I use pi underlying to denote Mackey functor and the 5-pointed star to denote ROG gradient. So I apply pi underlying star to the slice tower. This is a ROG graded slice spectral sequence we study. So in this talk, for simplicity, I will focus on the Z-graded slice spectral sequence, but our theorems are proved for general ROG graded version. So here is an example of a C4 equivariant slice spectral sequence of BPC for one. We can see node D is inverted, so this Bott class D is not inverted, so this is a connective theory, and it only has one cone. So from now on, we work too locally. And the first question people ask when we have a tower is that what are the E2 pages of the spectral sequence? And so this is a Hopkins Ravenel slice theorem. So if G is cyclic 2 group and X is BPC2N, then the fibers of the slice tower, in other words, the associated gradient, are wedges of the following form. So HZ is an equivariant Albert-MacLean spectrum, where Z is a constant Mackey functor. So we suspend this spectrum by some regular representation sphere and induce it up. This gives us summations of the fibers. So if we apply pi star to it and play with adjunctions, we will see that this is just the C2I equivariant homotopy group of HZ. A similar result hold for the truncated version of BPC2N as well as the periodic versions. So the first task is to understand this homotopy group, and this will give us the E2 page. So now I will introduce a new method of computing the E2 page using the generalized Tate diagram. So firstly, I will present some results. So using this new method of generalized Tate diagrams, the ROC4 graded homotopy green functor is completely determined. The green functor is just a Mackey functor with multiplicative structure. And in general, when I try to understand the homotopy of HZ for general C2N, but the extension, from the experience of the computation, in the C4 case, the extension problem in this Mackey functor is very complicated. So it's very hard to get a complete answer for ON. But we have the following result. So with equal Sikora, so we computed the positive and the negative cones of the C2N equivariant homotopy of HZ. So these positive cone and negative cones will give us the E2 page of the Z-graded slice spectral sequence at least. So if we look at this series, and if we only care about Z-graded spectral sequence, then this result will tell us how to draw the spectral sequence for O, M, and N. And so before I introduce the method, I will start from some brief history on this equivariant computation of HZ. So Louis Stone computed the CP case where P is odd. And Dagger and Greenlees computed the C2 case independently. So in the case of HZ, the C2 case is a little bit more complicated because we have the one-dimensional sign representation, which is non-orientable. But for CP, we don't have non-orientable representation. So Zeng computed the homotopy of Z for the group P squared when P is odd. So Nick G computed the C4 case using his computer program. So this is a very complicated computation. Now our new method is about the generalized Tate diagram. But now let's recall some classical Tate diagram. So this is a classical Tate diagram by Greenlees May. The E is a G spectrum, and the square on the right-hand side is a pullback square. And the great thing about this Tate square is that we know a genuine homotopy type is very hard to understand, but this pullback square decomposes E into simpler pieces. So this part in the middle of the bottom, this is the Borel completion of E. And people know that this only depends on the underlying spectrum of E with a G action. And the other part is a localization of E. So this part has better periodicities. So this diagram decomposes E into simpler pieces, the homotopy completion part, the localization part, and they are glued along this Tate diagram. So here, this EG tilde space is defined just by the co-fiber sequence. The EG is a CW complex with free G action, and its underlying space is contractible. So EG tilde is defined as a co-fiber. And so now F is a family of subgroup. Greenlees may also have the generalized Tate squares. So by a family, we just mean a subset of subgroups of G under some closure properties. So we have a similar diagram, but the decomposition is different. So E is decomposed into this part. Usually people call this the F completed part. The other is the F inverse localized part. And this information is glued along the generalized Tate spectrum. So the great thing about this F completed part is that it only depends on the so-called F homotopy type of E, which is some subgroup level information. And this localized part has better periodicities. So this also provides a way to compute E using simpler pieces. So here again, this universal space EF plus is also completely characterized by the fixed point data. So the fixed point is either S0 or a point. And similarly, this E tilde F is defined as a co-fiber. So now let's start our computation. So if we look too locally, we can choose ROC2N to be this following free abelian group. So this is a real representation ring, and the elements listed here are irreducible real representations. One is a trivial one-dimensional representation over R, and alpha is a sign representation. It's also one-dimensional. And lambda 0 is rotation by 1 over 2 to the n of the plane. So it's a rotation of the biggest order. And all the other lambda i's are tensor powers of lambda 0. So they are rotation of smaller order. So now I propose a method to compute the ROC2N graded homotopy of any C2N spectrum using the generalized Tate diagram. So here we denote the generator of C2N to be gamma. Then we have a chain of family of subgroups. So we start from the empty set. So then we have the next smallest family is the trivial, the family with the identity. And then we include one group and get another family until we arrive at this family of proper subgroups. The P is a family of proper subgroups. And then we arrive at the biggest family, the family of all subgroups. So now we give some name to these families. So denote the family from the trivial group to C to I by Fi. And then this chain of family inclusions give us a chain of maps between the universal spaces. So recall that these spaces correspond to localizations. So this is actually a tower of localizations. Not only in the abstract sense, but also in a concrete sense in this case, because these universal spaces have very good models. So this universal space is modeled by the infinite dimensional sphere. So this is just, so lambda I is a two-dimensional rotation. We take a countably infinite many copy of lambda I and one point compactify. So, or defined in another way, S infinity can be defined as a co-limit along all the inclusions. So S lambda I has the north pole and the south pole. S0 includes into the two poles, and we can iterate this process to and take the co-limit to define S infinity lambda. So smash any C2N spectrum with a chain of families, we get the following tower of localizations. So the right-hand side is the easiest one to understand. So if we take fixed point of this tower, the rightmost fixed point is the geometric fixed point. And in general, the geometric fixed point is much easier to compute than the genuine fixed point of X. So this tower gave us a bridge between these two type of fixed point. And we can start from the easier one and do some backward induction. So we start from X, A alpha inverted, and then delocalize one step at a time until we arrive at X itself. The fixed point of X with A alpha inverted is the geometric fixed point. And since we will apply our computational method to HZ, the input for us is computed by Hill, Hopkins, Ravenel. So the geometric fixed point of HZ is completely determined. And we can start from there and start our backward induction. So how do we do this backward induction? So assume we know the homotopy group of E tilde Fi is match X. By that backward induction, we can assume that. And now we want to understand the E tilde Fi minus 1 match X. Using the Tate diagram, it is enough to understand this Fi completed part of this homotopy group. And we know that, so for example, in the case of EG, this universal space has only 3 cells. So it only depends on the underlying homotopy type. But in general, this Fi can be decomposed into cells with smaller groups. And so by induction on the group order, we can also get a spectral sequence compute this part. And the spectral sequence comes from the cellular filtration of EFI. So we can compute the homotopy group of this spectrum by, there are several different names of this spectral sequence. We can call this Fi homotopy limit spectral sequence, or the equivariant RTF first root spectral sequence. So let's see the computational result. So firstly, recall some C2 equivariant computation. So this is computed by many people. So in this case of C2, we have, so ROC2 is a rank 2 free abelian groups. The star plus star alpha, where alpha is a sign representation. And it has a presentation as follows. So we have a nice part, the polynomial part, generated by U, which people call an orientation class, and A people call the Euler class. And the rest of them is a little bit messy, but not that bad. So these are called the negative cones. So they will appear in the negative cones of the slice spectral sequence. So here, just their corresponding degrees of the elements. Now, when G is C4, ROC4 is a rank 3 free abelian group. We have a trivial representation, sign representation, and the rotation by 1/4 of the plane. And correspondingly, we will have 2 Euler class and 2 orientation class. And applying the method, so we have, so the top level of the green functor is as follows. So we have these many classes as well as the following classes. So as we can, so this thing become a little bit more complicated, and we still have this good part, which is the polynomial part, and this is the positive cone. The polynomial part contains some relation, which is discovered by Hill, Hopkins, Ravenel, called the gold relation. So it's because it involves relation between the A and U's. The rest of them, so not every, if we only care about the Z-graded spectral sequence, not every class will appear. So these are the mixed degrees. So the orientation, one of them has negative power, another has positive power, and this will not appear in the Z-graded spectral sequence. So these classes, where both of them has negative powers, or these classes, where all classes has negative power, they will appear in the C4 slice spectral sequence E2 page. In the following sections, we will apply the Tate diagram to the slice tower of X. The Tate diagram can be applied to a G spectrum, but can also be applied to a tower spectrum. And this will apply this to the slice tower and give us a way to compare different spectral sequences in this Tate diagram. And the duality of differentials I mentioned before will be deduced from this Tate spectral sequence over this corner. So BPC for 1 is a motivational case. So in the above computation, I also computed the following corresponding part of the E2 page of the related spectral sequences. So we have the localized homotopy group of HZ, the Fi completed part, and also the Tate construction of HZ. Now we can talk about the duality of differentials using the Tate spectral sequence. So as mentioned before, the goal of our project is to systematically study and explain the duality pattern in this picture. And the result is that the duality pattern actually come from the periodicities in the Tate spectral sequence. And to motivate this thing, we can start from some simpler computations. So this is the C2 slice spectral sequence of KR. And we can see that the differential patterns are pretty simple. So in the positive cone, we have just one type of differential, D3 differential. And actually the essential input is only here, the first D3 differential, and all the rest can be deduced from multiplicative properties. And in the negative cone, similarly, we also have only one type of differential. There are many ways to deduce the differential in this spectral sequence, and one way is to use the 8 periodicity of KO, because we know the spectral sequence compute the fixed point, the homotopy of the homotopy group of the fixed point of KR which is KO. And we know the homotopy group of KO. It should be Z, Z2, Z2, 0, Z. So Z, Z2, Z2, 0. And this part should be 0. So this black dot must be killed. And this is how we deduce this differential using a periodicity of KO. And similarly, we can deduce differential here. But the thing is, computing using periodicity is hard to generalize because when we consider this higher height theories, their periodicity becomes bigger and bigger. So for example, D inverse BPC for 1 has a period of 32. And if we do a similar C8 equivariant spectrum, then it has period 256. So using periodicity is not the best way to understand it. And also periodicity is only on the homotopy group level. It doesn't tell us a duality of differentials. It just tells us finally the groups are isomorphic. So we want to find better ways to understand this duality pattern. Now we can look at this thing from a different perspective. So now on the left-hand side is still the slight spectral sequence of KR. And on the right-hand side is the Tate spectral sequence of KR. There is only one non-trivial family for C2, and this is just the classical Tate spectral sequence. Now, if we compare the positive cone of the slight spectral sequence with the corresponding positive cone of the Tate spectral sequence, we will see that they are actually isomorphic, except on the 0 line. So box means the Z, and because the Tate spectral sequence is 2 torsions, so this map maps Z to Z mod 2. So except that their positive cones are isomorphic. And similarly, if we compare the negative cone of the slight spectral sequence on the left and the negative cone of the Tate spectral sequence, they are also isomorphic. And the Tate spectral sequence gave us a bridge to deduce the duality phenomenon in this slight spectral sequence itself. And where are the comparison maps coming from? And we look at the Tate diagram. So now, firstly, we want to compare the positive cone, and there's a natural map from the slight spectral sequence to the Tate spectral sequence. So we map to the geometric fixed point, and then map to the Tate fixed point. So this composite will give us the isomorphism between the positive cones in these two pictures. And what about the negative cones? So we have to go another way around. So we start from the Tate spectral sequence using the connecting homomorphism. So because of vertical maps forms a co-fiber sequence, we have a connecting homomorphism go to there. And then this is a pullback, so the top arrow is invertible. So we go from the Tate spectral sequence to the vertical fiber, and then compose with the inverse, and then go back to the slight spectral sequence. And this comparison induces the isomorphism in the negative cone we see over here. And actually, this kind of duality is a thing that generalized to bigger groups, thus to bigger heights. So now we take a general cyclic 2 group. So the setup is that we have a general cyclic 2 group, and X is the general form of D inverse BPG M. And recall our notation that Fi is a family from the trivial group to C2I. And then we consider the comparison between spectral sequences induced by the two composites. So in the positive cone, we have a map from the slight spectral sequence to the Tate spectral sequence. And in the negative cone, we have a map from the Tate spectral sequence from here, go to a vertical fiber, and then compose with the inverse of the top arrow, and go back to the slight spectral sequence. And the two composites induce isomorphisms between the slight spectral sequence and the Tate spectral sequence in dual cone regions. So by dual, I mean the opposite cone regions. And it's easier to see from examples. So here, we will show this C4 slice spectral sequence of D inverse BPC for 1. If we look at this region bounded by the diagonal line, the line of slope 3, we will see that these dual regions have the same type of differential, which are all blue differentials. And if we compare this light spectral sequence with the Tate spectral sequence, we will see that these blue differentials can be interpreted by the periodicity in the Tate spectral sequence. So this Tate spectral sequence has periodicity along 2 directions. So actually the essential input is only one non-trivial differential. Now we can look at a little bit more complicated picture. So we look at the region bounded by the diagonal line and x-axis. The differential here is more complicated than before, but they are similar to the dual regions. And we compare this diagram with the Tate spectral sequence. We will see that the positive cone is isomorphic to the the positive cone in the Tate spectral sequence, and similarly for the negative cone. And now this duality pattern, so the underlying reason for the duality pattern come from the periodicity in the Tate spectral sequence. And we prove that the Tate spectral sequence has enough periodicities. So still the same setup, G is a cyclic 2 group, X is the theory, Hill-Hopkins Ravenel theory, and F the family from E to C to I. The Tate spectral sequence, Fi Tate spectral sequence will die at a finite page. So that tells us all the differentials have bounded lengths. Secondly, we can always find at least 2 unit class in the Tate spectral sequence, and they point to 2 different directions. So let's see the pictures. Okay, so combined together, this means the dual cones of the Tate spectral sequence contain the same amount of information. So let's see from concrete examples. So G is C4, and Fi is the family containing E and C2. So we have some periodicity class. It's easier to look at them from the pictures. So one of them is pointing towards 1, 3. Another is 4, -4. So the repeating patterns in this Tate spectral sequence is explained by the periodicity, 2 periodicity class, because as long as we know one non-trivial differential, for example, this one, then we can just propagate the differential along 2 directions to get the whole Tate spectral sequence. And now we can change our family. So F0 is a family with a trivial subgroup. Now we also have enough periodicities. So we can choose these 2 classes to be the periodicity class. The first class in degree 8, 8, another in degree 32, 0. So this 2 periodicity tells us that the essential information of this spectral sequence is contained in this parallelogram. So there are 2 classes, and if we draw a parallelogram spanned by them, then all the differentials is contained in this parallelogram. So because the 2 cones of the Tate spectral sequence are infinite regions, and the essential information of the Tate spectral sequence is contained in a finite region. So they literally, both cones literally contain the same amount of information. And this explains the duality in the slice spectral sequence we saw before. So for example, this is the slice spectral sequence. And how do we deduce differentials in the negative cone from the positive cone. So we can start from this pink differential in the positive cone. And this will give us exactly the same differential in the Tate spectral sequence because they are isomorphic in this region. And now imagine we are in the Tate spectral sequence. So we have a whole plane spectral sequence, and we can move differentials around. So here we use -32 periodicity to move this pink differential to this differential in the second quadrant. And then we have another periodicity, -8, -8. So we can move this differential along this direction and arrive at this pink differential. So this differential are dual in this sense. And we can play this game to other differentials and get all the pair of differentials using the Tate, the periodicity in the Tate spectral sequence. So now there are also some transchromatic phenomena in the slice spectral sequence. So we can see from the picture that either in the positive or in the negative cone, the spectral sequence is divided into two regions by the diagonal line. So above the diagonal line, everything is very nice and simple, and below this diagonal line is like a more complicated world. And this is a transchromatic phenomenon in the slice spectral sequence. So here we can look at a C2 equivariant slice spectral sequence of KR. So these are all D3 differentials, and if we rotate this positive cone by 45 degrees, we will see that this pattern over here is exactly the same as the pattern over here. And similarly, if we look at the negative cone, these are all D3 blue differentials. And in this bigger slice spectral sequence, there are D5 differentials. And Meier, Shi, Zeng first proved the transchromatic isomorphism in the positive cone. So in plain words, that says like the slice spectral sequence of the lower height theory is contained inside the slice spectral sequence of the higher height theory. So when the group, so this group on the left-hand side is C2n, the group on the right-hand side is C2n plus 1, so the height is multiplied by 2. And they prove this thing for the connective version of the theories. And the differential is also, there are also correspondence between the differentials. So a dr differential is stretched to a d2r plus 1 differential. Like, yeah. So now, my collaborators and I are utilizing the entire Tate diagram. So we use the Tate spectral sequence as well as a vertical fiber in the Tate diagram. And using these, all of these comparisons, we prove the transchromatic phenomenon in the negative cone. So in the stems, where the stems are smaller than 0, then the slice for the periodic version of Hopkins Ravenel theories, the slice spectral sequence of a lower height theory is contained inside the slice spectral sequence of a higher height theory, as we have seen here. So in the negative cone, these blue differentials will sit inside the blue differentials in this region. Also, the length of the differential will be stretched. Now we can conclude this talk by an inductive way to compute the slice spectral sequence. So this is a slice spectral sequence of a periodic theory. And by the transchromatic phenomenon in the positive and the negative cone, we know that all the all these regions of red, yellow, or green color, they are known by induction. And in the negative cone, this red, yellow, green cones, they are known by induction. And because of the differentials here, not too many classes will be left in these regions. So it simplifies the work for the blue region. So in this blue region, we can use our duality of differentials we proved. So for example, if there is some differential in the positive cone that is easier to compute, then we compute this one and just deduce the dual differential in the negative cone immediately. Or for some other reason, some differential in the negative cone is easier to compute, then we can use the duality of differentials and move this differential in the negative cone to the positive cone. And this will greatly simplify our computation for bigger groups. So thank you for your attention.
Thank you very much.
Thank you.